the whoever. Okay. Okay. So we are going to start talking about transformers. And so this is basically a transformer. So you have encoder and decoder. We'll go in detail. And we'll cover the basics. What is a transformer? Self-attention, the most important thing in transformer. There's a notion of query, key, and value, and then position encoding, and then encoder decoder architecture, as you see here. And the bird.
Sure, there is a query, it is cutting in the online video.
Yeah, that's the thing. I don't know how to. So how, because I think it's only showing the green, and right? So who's expert in these things? How do we do that? Shall I just share the screen maybe instead of sharing the
Yes,
window?
share the screen.
That'd be best.
Okay, so share the screen. Okay, let's do that. Okay, how about now? Now it's good?
Now it's good.
Okay,
That's
very good.
perfect. Thank you.
So we're going to talk about BERT, which is, one of the earliest transform model, pretty useful, famous. And then we'll talk about vision transformer in particular, because the transformer started from NLP, and vision transformer, we talk about VIT, and then we are going to talk about SWIM. Okay. So transformer is used for modeling the long dependency between the input sequence. So you have a sequence like a sentence, you have a sequence of words. So it will look at the long dependencies between, given a one word, look at the all other words and look at their attention and so on. So it is better than LSTM, long short-term memory, which are called recurrent neural network. You must have learned in the computer vision class. This will transformer does everything in parallel. Okay, so so therefore, and also it is can be used for multiple modalities, like you can use for, of course, language, you can use images, video, text, speech, and all those things. Very similar idea. So transformers are typically pre-trained on one large data set, then, and typically it's in self-supervised manner that you don't need a labeling, and which means, can be unlabeled data set. Then we can use that for downstream tasks for different things we want to do. So it is pretty, good performance. Is, it can be scaled, large networks, huge data set. And suppose GPT, everybody knows ChatGPT. So GPT stands for Generative Pre-trained Transform, right? So this is the backbone of GPT is the transformer. So very important concepts, which, which we will cover that in this course, and you need to fully understand that. Okay. So it has been widely used in computer vision application, image classification, object detection, action recognition, segmentation, because originally it started, we were using CNN, convolutional neural network. Now, most of the things we are able to do using transformer, especially visual language model, because for the NLP, the transformer is the thing to go. So therefore, if you put vision, images, video, then we want to use transformer for that also. Okay. So it can be used for generative modeling, multimodal tasks, like visual question answering, as I talked about first lecture, visual reasoning, visual grounding, and it can be used for video processing. We can recognize activities, we can do video forecasting or prediction, and for low level vision, like image super resolution, image enhancement, colorization, and 3D analysis. You can use transformer for the point cloud, where you have 3D information, each point has X, Y, Z, and you can use for classification, segmentation. So of course, it started in NLP. So BERT is the one of the most famous transformer applications, got bidirectional encoder representation from transformer. You will hear BERT a lot. So GPT, as I mentioned before, Roberta is another transformer, robustly optimized BERT pre-training, T5 from Google, text-to-text transformer, there are 5 T's here. And so basics are that we have encoder and decoder blocks transform. Okay. So main components of each block, we have self-attention. That's an very important concept, and I'll explain in detail. And then we have layer normalization, and then we have feed-forward network. So those are the kind of 3 things in transformer, encoder, decoder. So encoder may look like this, that we have input and we get some embedding, get representation of feature vector. Then we add to that the position encoding. And then we have this multi-head attention. After that, we have ADNOM. Then we have fully connected layer and ADNOM and the output. So this is encoder. Now decoder is very similar. Okay, so as you see that multi-head self-attention, ADNOM, multi-head attention, ADNOM, and fully connected layers, ADNOM, and then we have output, the probabilities. And this one is the softmax. So now we'll go in detail a little more. So if you look at this one, we have multi-head self-attention is basically looks like that. So we have a query, key, and value. Okay, so this goes to scale product attention. We concatenate this, and we come out from here, multi-head attention. And we go through detail, so just don't get concerned. So here is the scale. This operation is explained here. So we have query and key. We'll multiply to matrix multiplication. We'll scale it. We can sometimes mask some of those tokens, and then we have this softmax, and the value comes here. Then again, matrix multiplication will come out. So this is the scale dot product attention. So now let's look at the self-attention idea. So in transformer, we deal with tokens. So each word is like token. You can consider each word in a sentence a token. So hi is one token, how is another token, or is, we have 4 tokens. Okay. So we will take each of the word and get some feature representation, some vector. Word to vec is common way to get some feature vector. So we will call this one x1, x2, x3, x4. So we have 4 feature vector of this each of the word. So the basic idea of self-attention is that we are going to take each of the word and find a dot product with every other word, including itself. So this will be the dot product of first token with first token with second token, first token with third token, first token with fourth token. So we'll get this. And this will be the second token with first token, second token with second token, second with third token, fourth token. So this is a matrix we get. Okay, so this will look at the cosine similarity, how similar this first token is with second token, third token. So that's, we want to pay attention. If it's very similar, we pay more attention. Okay, so now, so again, this is what we have. So x1, x2, x3, x4. And so typically, so we'll get these kind of values, when we do that, cosine similarity. We can normalize, we can do that. So now what we are going to do taking this matrix W, and we have this representation, which is X, then we are going to multiply each of this with this matrix, and this will be our output. So we will do these. We have 4 tokens, X1, X2, and 4, and we'll multiply that, and this is with X transpose. So therefore, Y will become this matrix multiplied by X transpose. So that is saying that we started with X1, X2, X3, 4. We got how similar each token with the other, so we multiply with that to get a better representation, which is shown in the green. So that's very simplest idea. So we'll build upon that. So now in that, so far we haven't learned anything. Yeah.
For each of those vectors being multiplied individually?
Yeah, we'll multiply this vector with this vector with this vector with this. So I'll explain more detail. So now in this one, as you saw, we just took the representation and multiply each token with all other tokens. We got the values and then multiply with this one. Okay, so there's no learning. It just depends whatever value are. We took this one, multiply with that. Okay, so now because the whole thing in deep learning is learning, that we want to learn, we want to determine these unknown parameters, and that's what the main thing is, deep learning. Okay, so we are going to now do the learning. Okay, so now this was, abstraction, how are you, whatever, those were words, vector. So now we are going to look at the images. Okay, so let's say we have a 3x3 image. It's a RGB, right? We have 3 channels. So in this one, we are going to consider each of these as a token. So we have 1 token, which is, this one, second token, this one, like that. So each token is 3-dimensional vector, and total we have 9 tokens. Yes. So now we are going to do this a little more, sophisticated way compared to what we explained earlier, where we will introduce learning, and learning will be with these 1-by-1 convolution. We'll have the K convolution and query and the value. So we will take this 3x3x3 and apply the 1-by-1 convolution to each of these token, and we'll get this. And 1-by-1 convolution to this one, we'll call the query, this will be key, and similarly value. So 1-by-1 convolution that we will learn, like as you have done in the computer vision course. Okay, so once we get this, then we'll take the transpose of this and multiply with this and apply the softmax. We will normalize these numbers up to 0 and 1, and this will be our attention map. Very similar W matrix I showed you. Suppose right now here we have 9 tokens. Okay, so it's the first token, second token, third, 9 token, and this says that how much attention first token has to itself, then second token, third token, fourth token, 9 token. So this attention map. So then we'll take the attention map and multiply with V, and then after that we'll do one more 1-by-1 convolution and get this. So that at the end we started with 3x3x3 image features. We get 3x3x3 image features, but these are better because this has self-attention. So we are giving importance of each of the feature depending on how much support they get from other tokens. Okay, so in this one we are learning, when we learn these, 1-by-1 convolution here, here, here. So 3 of those and one more, 4 1-by-1 convolution. Okay, so that's basically is a self-attention applied to simple 3x3 by 3 image. Okay, so let's go in more detail. So the difference here is, as you saw in the previous one, we are not learning anything, okay? We were just multiplying and getting, but here we are learning, so that's the main thing. And in deep learning, we have to learn, everything we have to learn. Okay, so now, so these are the 1x1 convolution. Now, 1x1 convolution applied to this 3x3x3. How many parameters will that have? 1x1 convolution. Anybody can tell me? If you apply 1x1 convolution to this one, how many parameters that mask will have? 3, right? 3. So we'll have 3 parameters, 1x1x1, because we have 3 channels. So therefore, we have 3 parameters we learn for this one, and similarly 3 parameters for this one, for 3 parameters for this one. So these are, so far, we will learn 9 parameters to do this 1x1 convolution from here to here. You take this one, do 1x1 convolution, you will get this output, and we will learn 3 parameters for this. Similarly, from here to learn, apply 1x1 convolution, we get this one, again, 3 parameters and 3 parameters. Yes? Okay, yes.
Do we use a bias in the convolutional
Huh?
filters? Do we use
No,
a
it's
bias?
just a simple, just, 3 parameters. We don't have to do bias, okay? So then we have the last 1x1 convolution, we have 3 more parameters. So that's what we have done. So let's now look at more, a little bit more detail. So we will denote, we have n entities, n tokens, right? In this case, we have 9 tokens, yes? And so X is the Rn by D. So the n is number of tokens. We have 9 tokens. In this case, D is 3. Okay. So this is a matrix. So we can explain that using matrix or a convolution. There, we can go back and forth. So now we want to get the WQ and WK and WV. So these are what we want to learn. And this will be D by DQ and D by DK and D by DV. And we are going to assume that DQ and DK is same, okay? So input sequence X, we will take the X, multiply by WK, we'll get K, take X, multiply by WV, we get V, and then we want to come up with Z, which is the output here. And the way we are going to do that, Q, K transpose, divided by the dimension of this DQ, and then softmax, then multiply with V. Okay, that'll become Z. So that's the way to write an equations matrix, or the way, well, explain in terms of 1x1 convolution, but they are the same. So we can look at actual values here. So in our case, we have X matrix is 9 by 3. Yes, we have 9 tokens, each is 3 dimensional. Then our case, the WQ will be 3 by 3. Okay, WQ is 3 by 3. So then this will be, WK will be also 3 by 3, and WV will be 3 by 3. So therefore, we will get these numbers now. We have to do this. Suppose we start with 9 by 3. So then this will be, yeah, actually I did a mistake, and I think he was right. Because what I explained to you before, 3 by 3 convolution is 3 parameters, but we have to get 3 channels. So which instead of 3, we have 9 parameters. Okay. So, so that's what is happening here. So as you see, WQ is 3 by 3. So because we have 3 filters, 1 filter for first channel, second filter for second channel, and third filter for third channels. So that's what we have here. So therefore, Q is obtain by multiplying WQ, which is 3x3 matrix, with 9x3, which is our original, what we start X. And similarly, if you multiply 9x3 matrix with 3x3, we'll get 9x3. Okay. And similarly, K will be 9 of 3, and V will be 9 multiplied by 3. So now we take the Q and multiply by KT, and this will become 9 by 9 because this matrix, as you see, Q is 9 by 3. K transpose will be 3 by 9. So therefore, 9 by 3, 3 by 9 become 9 by 9. And then V is 9 by 3. So then we will get 9 by 3. So that's a way to describe the self-attention in terms of matrices, the equations. And then you can also describe in terms of convolution filters. So therefore, we will have the 9 parameters for the WQ, 9 for WK, 9 for WV, and then we have the last one, which is this matrix. We have 9 for that one. So that basically is self-attention. And this is very important. You need to understand the math, the matrices, and also the convolution. Yes.
Can you just like explain the 3x3 part?
Yeah.
That's what's confusing me.
Yeah. So I think what we are doing here, we have these tokens. So X1, we can consider this is 1 pixel here. There's 3 channels. So this is 3 by 1 vector. Then we took a second one, another 3 by 1, another one 3 by 1. So we have 9 those tokens, and each one is 3 by 1. So therefore, X is 9 by 3. So we put in the rows, first token, second token, third token, 9 token. So that's our matrix. Now we want to, from that matrix, X matrix, we want to apply this another matrix, which is 3 by 3, to get the query. Okay. And this WQ
Oh, so
is
we're just making it 3 by 3 because we want the output.
yeah, I mean, no, yeah, because see, the first is it's limited to 9 by 3 because input is 3. So it has to be 3. Yeah.
So we're basically just doing like an identity.
Yeah. No, it's not identity.
In size.
It's the same size. So here it has to be 3 because it's 9 by 3. Now, if you want, you can do different here. The next one, it can be 3 by 4 and so on. But we want to actually start with this one, which is 9 by 3. We want to end up with 9 by 3. So that's why it has to be 3.
So if this was like a 9 by 4, then would that be a 4 by 4? Or...
Yeah. Because you see, you have to look at what's the input, what's the output, right? So we want to take the 9 by 3 at the end. We want to come out with 9 by 3. So this is 9 by 3. This is 9 by 3. 9 by 3. 9 by 3. Okay, and this is 9 by 3. So you maintain that. So idea is that you take these features, we want to improve the features. And the way we improve the features, we want to get the support of each token from all other tokens. If they agree, they become more important. So that's the idea. Okay. Any other question from the also online? Do you guys have any question?
So when we're looking at these, we're
Unmute and start talking.
yes, can you hear me?
Brian, you are talking something, we cannot hear you.
How about now? Can you hear me? Sorry about that.
I can
Okay,
hear you.
yeah, now we can
Okay.
hear you, yes.
Okay, sorry about that. So we're assuming each pixel is a token and each pixel has 3 channels. And so we have
Yes,
the 9
that's right, yeah.
tokens. So it's
Mhm.
almost like we're unrolling this image, so to speak, and then we're passing each pixel as a token into the self-attention.
Yeah,
Just wanted to
yeah.
recap. Okay.
yeah. So this is a very simple example to build the concept, but we'll go, later where each token will be 16 by 16 page. Okay. So it won't be 1 pixel, because if you take a long, big image, if you keep doing for each pixel, will be a lot of computation. So that's why, each 16 by 16 page in the VIT will become 1 token. Okay, but that's the idea. Any other question from the virtual class?
I have a question about the 1 by 1 pointwise convolution. Does that
Yes.
create the learnable parameters?
Uh-huh.
Okay,
Yeah, so see that you know that in order to get this first channel, so we start the 1 by 1 convolution. So since input is 3 channels, so we will have the 1 by 1 by 1. So we will have 3 parameters there. So we'll apply a mask, which will be 1 by 1 by 1, and multiply with this first token, we'll get the first animal here. Similarly, we take the same mask, apply the second token, third token, we'll get the first channel. Now we want to get a second channel here. So we'll have another 1 by 1 by 1 mask we'll apply to each of these, we'll get second one. And we'll have third one, we'll apply this one, we'll get this one. So that's the idea when you write the PyTorch code, that's what you are doing. Okay, the convolution. Okay, is it clear?
yes, it's clear. Thank you.
Okay, thank you. So, okay, let's continue this. So now this whole thing started from this famous paper. It was called Attention is All You Need by Google authors. And right now it is 100,000, more than 100,000 citations. And it was published in 2017. Okay, so it's a big impact. And there are lots of resources for the transformers. These are a couple of them, and I'm going to build upon these. I'm going to use their slides and so on. So by the way, so we will put all the slides on the course website. We already put in the web courses first lecture, so you should be able to access, and we'll also put the video. Okay. So and I'm leveraging the slides from this professor also. Okay, so transformer, let's go in detail. So here we have, okay, how do I move this thing over here? So we have, let's say we have, so I assume it's a French sentence, and we want to use transformer for translation, machine translation. You want to input this one and want to output this. I'm a student. Okay, French to English. So simple high-level idea is that we'll take this, we'll have several encoder blocks, and then output of the last encoder block will go to decoder. Decoder, again, we have decoder blocks, and we will do the cross attention here between the output of encoder and of this, and then we'll get output, which will be the I am a student. So now let's go into detail. So each of the block will have self-attention and the feed-forward neural network. Okay, feed-forward neural network. And so self-attention we explain. So the idea is that, well, let's say we have a very simple sentence, thinking machines. So we represent that in a vector, as I explained to you earlier. So x1, suppose here we have 4-dimensional vector. So it go to self-attention. After the self-attention, we call Z1, and this is Z2. Then we have feed-forward neural network. After that, we'll have R1. So again, the idea is that we have parameters here we are learning, and the feed-forward neural network with other parameters will learn, and that there'll be lots of millions and millions of parameters. That's what the whole deep learning is about. Okay, so this first block, we'll have second block, third block, we just keep going. So exactly same thing, second block will be like that. Self-attention, feed forward neural network. Okay, so now as you see that this feed forward can work independently of each word. So we can parallelize all these, and that's the whole idea. It's not a sequential. So again, let's look at a little bit more detail. So we have input thinking machine, just two words, two tokens, x1 and x2, we get embedding. We get queries, key, and values. And the way we get it, we take the WQ, multiply with x1, we get that WK, WV. So here 4-dimensional. So as you see, we have 4 by 3. So as you were saying, so earlier we have 3 by 3. So we can, depending on what you want. So then first we create 3 vectors, which, we have query, key, and values. And then by multiplying input embedding, which is this one, with these matrices, which I explained to you, WQ, WK, WV. And so this will look like that. We got X1, from there we got Q1, K1, V1, and we multiply Q1 and K, and we suppose we get number 112. And for this one, we get 96. Okay, so now the next thing we are going to do is this is your 112 and so on. Now we are going to divide by the dimension of our DK, under root of that. So that's the explained here as I explained to you earlier. So 112, since we're going to look at the divide by 8. Suppose we want DK to be 64 dimension. Under root of 64 is 8. And so from 112 will become 14. And then this will become 12. Then we apply softmax so that this and add up to 1. And then last step is that we'll do the V, which will be the 0.88 multiplied by V1 plus 0.12 multiplied by V2. So that's the whole, all these steps explained in this particular 2 token examples, the processing we are doing. Now here we just have vector, in the image case we have actually 3 values. Here just we have 1. So now other thing in self-attention is that this was just one head, but we will do this multiple heads because we are going to learn more parameters. In the example I gave you, we have 9 parameters for key, 9 parameters for value, 9 parameters for query, and 9 parameters later at the end when we are doing softmax and so on, right? So there were 36 parameters. So this is one head, but we can have many heads, and we'll again learn more parameters. And that's why when you hear ChatGPT has 7 billion parameters, that's where these parameters come from. Okay, so more you learn, then your system become more powerful. So now let's say we will have 8 heads. So the same thing, we just keep repeating, but in this sense, we will randomly initialize, so they will become different. Okay, so that's the idea. So we will have attention head 0, attention head 1, and 7. And then it will expand the model's ability to focus on different positions. And each layer will have the subspace and so on. So let's look at this one. So yes.
The number of parameters related to the number of data, or just how do you define that?
Yeah, number of parameters will depend on the, of course, as we said, that our input in the first example I gave you was the 3-dimensional vector here. As I explained, let's go back to this one, the image thing. So here we have image, which is 3 by 3 by 3, right? So and each token is 3 by 1. So, and we want to get the 3 by 1 here. So one limitation will be depending on input. This is a very simple example, but typically we have 64 dimension or you'll have 120 dimension. We are going to discuss that. So one number of parameter depends, one thing is upon the input. The other, it will depend on the what output you want. So in this case, 3, we want 3. So that's one thing. Second thing will depend on the heads. So one head, in this case, we talk about that we have 36 parameters. So now if you're 8 heads, so 36 multiplied by 8. Now this is one layer. Then we can have 16 layers. So that multiplied by 16. So you just keep going. Okay. Yeah. So, okay. So let's do that. So we did that. And we did this. Okay. So now multiple heads, we have 8 heads. And so it will look like that. So after we went through self-attention, we started with X, we get Z, and we have 2 tokens. Okay. So this is first token, the second token, and this is first head, second head, third, and like that. So then we want to combine them and we'll multiply with another matrix, W0, okay, to get the final Z. So this matrix will depend where dimensions 4 and we have 8. So that's the way it will work. Okay. So this will be 8 heads with self-attention, where we have this example. We have 2 words, 2 tokens, and each is 4 dimensional. So I think you should work this out at home to really understand and then relate to your coding. Okay, so just summarize, we have inputs sentence, thinking machine, we embed them. We decided we want each word to be 4-dimensional vector. We split in 8 heads. So we will have these matrices for each head, the 3 matrices. Then we have multiply by 8. And we compute the attentions, value, key, and query. And then we concatenate all those. We get the final one, which is this one. This is for first head, and similarly, we will have the second head and third head and seventh head. Then this matrix will multiply, we get the final one. So 8 heads, we will get this X, we will get C after the self-attention. Okay? Yes.
Is W0 the weight of the fully connected layers or part of the attention or the self-attention?
Yeah, I think it's a part of self. After that will be the fully connected. After that will happen. So so now let's look at the example here. So now let's say we have actually longer sentence. The animal did not, and all those. So each one of is a token, right? The tokens, and then we have now. So we are talking about just one layer now. We are going to have actually 5 layers or 8 layers. So in this case, we are showing it word, this get attention from all these other, and this thickness shows that how important it is. Suppose this is a tire, it gets more attention than compared to other. And these are the different heads. This is one head, the green one's another head, and so on. So this you can say that in a sentence, how these words are paying attention to, and we are going to learn that. We are not going to tell it how much, but we're going to learn that, which is important thing in deep learning. Okay, so now we can show here that now we are showing also different layers, different things here, and it become very complicated. So many layers, in each layer, many heads, combine all those will give us at the end encoding of this. Okay, so now, so self-rotation we are done. Now the next thing we are going to talk about the position encoding. Now, as you saw that each word is in parallel, process. It does not depend on sequence. That the first word we need to do first, then second word after that, a third word after that. It is in parallel because we are looking at all of these together. Okay, so it's called permutation invariant, which means if you take a sequence 1, 2, 3, and you permute it 3 to 1, it will output of the transformer will be same because it does not depend on the order. So due to that, we want to introduce the position encoding to capture that kind of order. Okay, so to determine the position of each word or the distance between different words, we want to do that. So what we are going to do is, as we talk about, then suppose this is a sentence, is a French, and we get embedding this one. We are going to add another vector of the same dimension, which we'll call position coding. And then this will be one which will go to the transformer encoder layers. Okay, so position coding is important thing in the transformer. And what that is, that we will generate a vector depending on what the dimension of your token. So what D is the dimension of your token. In our case was started with 3, then we talk about 4, and it can be 64 or 128 and so on. So the position encoding will be alternate sine and cosine, sine and cosine. Okay, so for the even it'll be sine, for the odd it'll be cosine. Okay, so and this is defined like WK, it's like a frequency of sine wave, right? So this 10,000 2K of D. And so here is, we'll go in detail of formula, but this is the way it looks like. Let's say we have 50 tokens, okay? So this is a position encoding, and the dimension we have 128. So this is a position encoding for first token. This is the position encoding second token, third token, and so on. So we are going to add that to each of the tokens, and that's called position encoding. Okay, and as you see, each one is separate, each one is different. So let's go in now a little detail about this. So let's say, again, we have the sentence, I am a robot. So here we have we have 4 tokens, okay? And this is index of tokens, K, 0, 1, 2, 3. So, and we are going to use this sine, cosine coding. So this is very important because these people who wrote a paper, the attention all you need, Vishwani and all others, they were Google. So, and that's a very foundational paper, as you see, 100,000 citations. So then, as you guys know, that these days, OpenAI is a leader in this, Microsoft and so on. So Google is kind of, not doing that well. So the story is that they call up the co-founder of Google, Sergey Brin, to start coding. So if you look at Gemini paper, he's one of the coder. So he had one meeting with Vishwani, the first author. He asked him that why did you select this, cosine, sine, position coding, and then he explained to him. So this is, big history of this, how this transformer revolution started and so on. But let's try to understand how it works, okay? So we have 4 tokens and we have index 0, 1, 2, 3, and we are going to use the sine, cosine alternate thing. So let's say now and we are decided the 4-dimensional vector, okay? For dimension D is 4, but you can have any, as we did, we have 128, you can do that. So now in this formula, we'll just put the k is equal to 0. So when k is 0, this whole thing is 0. Sine of 0 is 0, which is this one. And then here we have I0 for the sine, for cosine. Then we got I is equal to 1, and for sine, I is equal to 1 for cosine. So they'll become like that. So we'll once we have the k0, all this will become 0, sine of 0 here, regardless of I here, right? Because k is 0, if I is 0 or I is 1, doesn't matter. So that's why 0, 1, 0, 1. So first token position importing will be 0, 1, 0, 1. Yes, simple. So now let's look at when token is k is equal to 1. Okay, when k is equal to 1, then then we have we will take the value of I 0 for first pair, and then we'll take a value of I as second pair, and D in our case is 4. When k is 1, n in our case is 100, and 2I will become 2, and divided by D will become 4. So 2 upon 4 is 1 upon 2. So therefore it will become 1. So the sine of 1 upon 1, 0.84, cosine of 1 upon 1 is 0.54. So here, then we go I is equal to 1. Now the under root of 100 is 10. So 1 upon 10, sine of that 0.10, and cosine of 1 upon 10 is 1. So that's the way we are going to code, now the second one, we will have 0.91 minus 0.42, and so on like this. So this will be the position coding for each. Yeah.
What does the angle 100 represent?
N is equal to 100 is the big number we are going to select. In this case, I think as you see that how it's basically depend on the frequency of these sine and cosine. So how fast it's changing. The original formula, as I show you here, is this one. So these are the sine and cosine waves, and you can decide in this particular example is 100, but it's again can be learned and can decide it depending on the application. So every paper will give you this whole section that what are parameters they use. Okay, so this, I think you guys should go through and really figure it out, all these thing, how this position coding works. Now, this was the position coordinate fixed. Once you determine what is the k value, what is I, what is D, and all this thing. But position encoding can be also learned. So what we are going to do, we don't have to do sine cosine, right? We'll just initialize 100. In this case, when I show you here, so our token embedding is 128 dimensional. So we're going to initialize 128 dimensional vector randomly, and we'll learn. As we learn the K, Q, and W V matrices. So that's another way, learnable position encoding. Okay. That's that. So now let's look at the next step that we are going to. The important concept is called add and normalize. So this notion is layer normalization, and because we have these different layers of encoder or decoder, so we want to normalize input across the features. So you guys know batch normalization, right? You have learned that. So this is a batch. We have different, vectors here. So we are going to find out the mean of this and then standard deviation of this, and we will normalize, subtract the mean, divide by standard deviation. We will do that. So this way, this is a mean of this first element, mean of second element, and third element. These are our vectors. This is our page 1, 2, 3. We have 3 in a page. So now the layer normalization work other way, that we are going to find the mean of each of these vectors, and which will go this way, and also standard deviation, and then we subtract the mean from each of that and divide by standard deviation. That's the layer normalization, so that the input to the next layer is normalized with all these. So we have talked about thinking machine. We embedded X. We do the position coding, self-attention, add normalize, and so then the feed forward is the next thing, and then add normalize once here and once there. So the idea is that we, after self-attention, we get the output, then we take this back, which is the skip connection, and we add this with the output of self-attention with the original one and normalize, then we go to the feed forward, add normalize, so it's twice, and this is your first layer, first head. Okay, so so this is the way it's going to work. So this is encoder 1 block, encoder 2 block, and so on. So now we have here a decoder block. So decoder will also be very similar. So we have, again, self-attention, add normalize. Then now the only difference is that here, when we do the attention, we are going to take the encoder output and put in here. And this will be called cross attention. So that this is coming from the self-attention is that we take the same thing X, we get 3 copies, key, query, value, and we do multiplication, so on. But here, the input is coming from encoder, then another input is coming from decoder, and this will be encoder decoder attention. Okay, so that's the one difference. This is called self-attention, but this encoder decoder attention, it's called cross attention because they are not the same. So that's the main difference. So that will be decoder block, then linear softmax. So the key and value will come from the encoder, and the query will come from the decoder. And in the self-attention, key, value, and query will coming from the same thing. Okay, so that's important. So you want to be clear about that. But the process is same. So we'll learn these matrices, multiply, transpose, and softmax, and all those things. Okay, so the BERT basically is the stack encoder blocks. So we have lots of these encoder block, as you see here, that we have multi-heads attention, add normalize, feed forward, add normalize. Then this one block, it's another block like that. That is the BERT. And so we are going to spend more time on the BERT. So the now the reason it's called BERT, bidirectional encoder representation from transformers. Now it's going to look at the both left and also right. So because traditionally look at sequencer, we look at the first word, we look at the all the previous word, we don't look at the next one, but here it's a bidirectional. So BERT is trained on two pre-test tasks in self-aware manner. One is a mass language modeling, and this is very important concept. So we are going to take a sentence, we'll remove some of the words and have the transformer predict what those words should be. Since we know the word we have removed, so we know what it should be. So it will predict something, maybe wrong. We will look at the difference between what it predicts, what's the ground truth, and we'll minimize that error. And that is where we are going to learn these parameters. Those parameters we talk about key, query, value parameters, and the other parameters we talk about. So it's called mass language modeling. And what we'll take a sentence, and let's say 15% of words we will mass out, make them null. And we will ask the encoder to predict. So as you know, it will randomly initialize parameters, it predicts something garbage. But we know what should be ground truth. We subtract between what is predict, what it should be. We take the loss and backpropagate that loss so that it learns better. At the end, it will learn what those words should be. So, so it will learn the context, bidirectional context. The second loss function we are going to use in BERT will be next sentence prediction. So we are going to take two sentences, suppose sentence A and B, and we will ask BERT to say if they are from the original document or not. So binary decisions like classification. Two sentences say, are they from the same document or not? So the way we are going to do is B is the actual sentence, which is next to A 50% of time, and then B is random sentence from for other 50% of time. So that's a way mechanism we'll have to learn these parameters. So BERT look like this. So we have, suppose, this sentence A, sentence B, and these are different tokens in sentence A. These are different tokens within sentence A, and this is their encoding. And then we are going to have the mask. It will predict the mask tokens, and this will be the next sentence prediction. This will be binary decision, 1 or 0. So that's the way we are going to work. So now GPT, which is actually stack decoder. So we'll take a decoder, stack together, it's become GPT. Okay. And as you remember, the difference between decoder and encoder is that decoder has a self-attention. Decoder has the cross-attention. So here is what is coming out in here. So if you compare with this thing I showed you before, here it was just itself, self-attention here. There was nothing coming out of. So in the GPT, we will get the decoder blocks we will have like this, but again, the format is same. The beauty of this transformer is at the end is very simple, right? So you have the input, your query key value, and you have multiple times of that. You have multiple layers, and that's the whole thing. Okay, so now that is about, I think, today. So I didn't want to spend more time, but it seems we will end here. Then we'll continue on Wednesday. We'll talk about specifically vision transformers.